slides from last time? Okay, got it. And that's optical polarimetry in astrophysics. That sounds a bit broad. I'm going to particularly talk about supernovae, kilonovae, and active galactic nuclei. And this work that I'm going to show is with these close collaborators. In particular, I want to mention Joao, Beatriz, and Ana, who are part of CENTRA and are actually here. So you can make all the hard questions for them. And so polarization of light, you know this very well. So basically you have the electric field and magnetic field that are perpendicular to the direction of motion of the light. And the electric field is what we use to know the polarization state. So if you were to measure random, you're going to see random directions of the electric field. That's when we say there's no polarization. And that's normally natural light. If you put it through a polarizer like here, you're going to see only one particular direction of the electric field. That's what we call linear polarization. But if that electric field is actually rotating, we're going to have circular polarization. Okay, and you can describe this in many ways. A particular way is the Stokes parameters, which are four. It's I, Q, U, and V. I is the intensity, so not really related to the polarization state of the light, just the amount of photons we have. Then you have Q and U, which are linear polarization. And for those that work maybe in CMB, this is similar to E and B modes and the CMB polarization. And what you do basically is that your plane of the electric field, you're going to divide it. You take a reference frame, let's say here, X, like you see there on the right. And if you compare the light that is with an electric field at 0 degrees compared to the one at 90 degrees, this is measured by the Q parameter. If you rotate that plane 45 degrees and you do the same, you compare your polarization state 45 degrees to 135 degrees, you have U polarization, and those two are linear polarized. This describes the linear polarization of the light. And then the V describes the circular polarization. Basically, you compare right-handed to left-handed polarization states. Okay. Then you can also have the polarization degree and the polarization angle. Basically, the polarization degree T is just going to be the squared sum of these three that give you polarization, right? So if you have 0 in each of them, you won't have any polarization. If V is 0, you don't have any circular polarization. And in fact, in this talk, I will talk mostly about linear polarization. And so basically, this is, if I don't have circular polarization, this is my linear polarization, the square root of Q and U. And the side angle is measuring between the Q and U, the direction of the electric field in those two components. So basically, it's important to remember that polarization is a vector throughout this talk. Okay, so what can create polarization? I already told you these polarizers that you can use in the lab, but one very common way to generate polarization is through reflection and scattering, and that's mostly what will be happening in this talk. But you're gonna also have and reflection creates linear polarization, whereas Faraday rotation, for example, and synchrotron radiation that also happen in astrophysics create circular polarization, but I won't be talking much about that. So scattering or reflection. So you have here in the cartoon, you have unpolarized light, right? That it's coming here and interacts with the particle. You can see it there as well. Basically, you have two polarization states. The electric field has to be perpendicular to the direction of motion, right? So when it's coming towards here, you're only going to have this polarization, and it's going to be linearly polarized, right? There's no particular preference for that direction, right? If you were to observe it on the other direction, you're going to have the same polarization state, right? If you observe it from up and down in this diagram, you're going to have also linear polarization, but 90 degrees, right? If you're behind, it's going to keep being unpolarized. If you have something in between, you're going to have partially polarized light. Okay, and so in this case, where you have an electron, so Thomson scattering, it's completely wavelength independent. That's very important. But it could scatter with particles, and some particles, like dust particles, they preferentially scatter in given wavelengths. So you're going to have a scattering or polarization that is wavelength dependent. Okay. So here in this talk, then I'm going to talk about these three topics that I mentioned, very different astrophysical systems. And at the same time, I'm going to be mentioning some of the problems that you can have when dealing with polarimetric data. And those are instrumental polarization, interstellar, and sky polarization. These kind of problems, I will talk about them. You have to deal every time deal with polarization data. So although I'm going to be presenting it at different moments after some of these other systems, they actually affect all of the three, okay? So let's start then with active galactic nuclei, or AGN. You're going to see a lot in the mention of AGN, and you probably certainly know this very well. The idea is that you have in some very active galaxies in the center, you have a supermassive black hole. So we're talking about 10 to the 6 to 10 to the 10 solar masses, supermassive black hole. That supermassive black hole is actively feeding material, so it has an accretion disk around it, right? And that's actually in this sketch right there in the center. But then you also have other components. So this accretion disk is actively feeding, and that's what powers this. These are very energetic events in the sky. And so you're going to see sometimes jets that are being emitted from the center region of this AGN, relativistic jets, and they go very far further out, very far from the galaxy as well. But then you also have another key elements of the AGN, which are what we call the broad line region clouds and the narrow line region. So in that sketch here on the right, you can see here the supermassive black hole, the accretion disk, and these are clouds of material that is being expelled from the accretion disk, or that is feeding in from here. Those are broad line region gas clouds, and I'll tell you why it's called broad line region. And then in the polar directions, you have narrow line region clouds as well. Okay, and then of course you have the dusty torus, which is very a lot of material that absorbs the light, obscures the AGN. And so nowadays, I mean, in the past we didn't know, we were observing a lot of things that look kind of similar, but we didn't know if they were the same. Nowadays we have what we call the unified model of the AGN, and basically what you had in the past is that you observe it from here. Now we know that it's an orientation thing, but in the past we were observing two different kinds of spectra, right? We had this, which is called type 1 AGN, and this one is called type 2. And so what you can see here is that these emission lines are coming from those clouds, right? And if you have broad components, so if you're looking from the top, basically you see both the narrow line region and the broad line region. That's why you see a thick part, but also a narrow part in the lines. That's a type 1 AGN. If you happen to be looking at it edge on, so basically from this direction, right, you're not going to see the emission of the broadline region, which is hidden behind the dust. So you only see the emission from the narrow line regions, and that's a type 2 AGN. That's why you see only very thin lines, okay, from these gas clouds. So, okay, it wasn't clear. Now we know that these come from the same, and it's just an observing point of view. And one of the key elements to figure out that this was the unification model, as the AGN come from the same, this type 1 and type 2 AGN come from the same object, is thanks to polarimetry. And I'm going to show you why. Here you have another, again, a type 2. So we're looking at it edge on, you only see emission lines. This is a typical flux spectrum, flux versus wavelength, okay? But then if we look at the polarimetry, the polarized flux, so basically the polarization degree multiplied by your flux, you actually recover the broad lines, and that's a type 2 AGN. So you may be wondering what's happening there. Well, the question is, we're observing it from here, right? But we know the light coming is actually coming from the narrow line region, but as the light from the broad line region here comes here, even if it's unpolarized, this light, it reflects, and I told you reflection of 90 degrees, this is going to get polarized. So indirectly, you're actually looking at the broad line region through the polarimetry. So that's why polarization can be extremely powerful. There's all these photons at the different wavelengths get the polarized states of polarization state. And even if it gets mixed up with light that comes from here, you still get a percentage polarization. So the degree of polarization tells you how much polarization, how much percentage of the light is polarized. And so now we know that these two types are coming from the AGN. So what else can polarimetry tell us about AGNs? This was already a long time ago that this was discovered. So now we're putting in question maybe actually the geometry of this dusty material, the dusty torus. And why is that happening? Well, if you look at observations in the infrared, this is emission in 8.6 microns from an AGN. This AGN is actually the accretion disk is in this direction. So this is the polar direction. And you see extra emission in the poles. And this is actually not expected. This is not expected. And what we can do is, and I will talk about 3D radiative transfer modeling during this talk. So I'm going to explain briefly what that is. Basically, it's a way you simulate photons and you simulate their paths. So in the case of an AGN, you know how the AGN emission looks like. So you generate a lot of photons with a given intensity and a given wavelength of that source. And then you model a dusty medium, and these photons are going to interact with the medium. So given this, the probability of interaction, it's going to either reflect. And so you do basically a Monte Carlo radiative transfer where you simulate all of these photons and you see how they arrive to the observer. And of course, you can also model what kind of instrument you're observing with. So this is a model of actually a torus, like the typical torus that we have. And this is what you expect, the sort of emission you expect. This is actually a cone, a hyperbolic cone. And this is if you have a perfect instrument, but we don't have perfect instruments. So once you include the perfect instrument, you obtain these two, on the non-perfect instrument, you obtain these two images that you see here. And you can see that this one, the torus, cannot reproduce the polar emission, whereas this one a bit reproduces. When you put, instead of a torus, you put a cone. So the question now is there a paradigm change in what we think AGNs look like? Maybe it's not a torus, but maybe it's a dusty cone. And what can polarimetry tell us about that? So you can also model with radiative transfer simulations what the polarization would look like for free structures here. So here's a hollow cone, a paraboloid shell. So this is a hyperbolic cone, paraboloid shell, and the usual torus. And see, so what you see here, these lines, these are the polarization predictions. So the longer the line, the higher the polarization, and the angle of the polarization is indicated by which by the orientation of those lines. And you can see that the prediction is different for different cases. You can even see that clearly, more clearly, if you integrate through the y direction. This is the integration in the y direction for 4 different filters or 4 different wavelengths, and you see that there is a clear prediction of the polarimetry being different for these 3 dusty structures. So we need data to compare with this model. And so we took extended polarimetric data. Extended means not just a point source, but we need obviously to take polarimetry at all of these positions to be able to say something about this. So, and we did this, and this is what we obtained. This is in R band, so a particular wavelength. And the brighter here, this is a polarization map. So the brighter points are more polarization. And this point here in the middle exactly coincides with the actual position of the AGN, right? But then if you look also here, so you kind of can see a bit of a cone right there, just by eye. And this part of this, so I shifted. This is, by the way, Circinus galaxy, which is Circinus AGN is the closest active galactic nucleus to Earth at 4 megaparsecs from us. And we know that this galaxy has actually a very disk like this, so we can only see the upper cone. The lower part of the cone of the AGN is hidden behind this. So that's why here, this is an unobscured part of the cone, whereas the part that is here behind the dust of the galaxy is probably light that is being reflected by the dust, light from the AGN that is being reflected by the dust, and so gets very highly polarized. That's why we see a high polarization on this side. And then you can see the obscure material of the torus or whatever it is, the cone on the edge, on the equatorial part of the AGN. So we can compare it in other different filters. This is the 4 filters. An image, you have an intensity in the color, but you have the polarization lines. And you can see that these polarization lines here are all on the side of the disk of the galaxy, very polarized, but also very aligned with the dust that is in front of it. And if we integrate this cone that is here that we know this is the size of a cone from oxygen-free emission lines. We compare here, this is the polarization we measure on these 4 filters as a function of wavelength. And we compare to different models, different structures of the dust. And well, first, you can obviously see that it is much lower. So there is, it seems that the data is not able to, or the models are not able to reproduce this data. But the reason for this is that you are getting a lot of depolarization, a lot of light from the galaxy that is non-polarized, right? So the AGN, these models are only AGN, but we have light of AGN and galaxy. So it makes sense that the polarization is actually lower. But what's interesting is that the wavelength dependence is actually closer to so some of these models are the torus, and this is the dusty cone, the hyperbolic cone, which sort of follows the wavelength dependence. But more importantly, the polarization angle is extremely in agreement with the polarization cone model. So polarization is probably telling us, look, at least for Circinus, this AGN, the dusty torus, what we always think is an AGN, maybe it's not right. Maybe you have to think about a dusty cone. So in all this, I'm ignoring all the steps that ignoring or just making the life easier, not telling you all the details of handling with this data. So I'm going to go to one of the first complications, and there's instrumental polarization. So it turns out that the polarization from the instrument itself is not zero everywhere, and you have to correct for that effect. And this is something we did for the Force 2 instrument in the Very Large Telescope in Chile. So it's an 8-meter class telescope with a polarization polarimeter instrument that I'm going to show you a sketch here. So the key element for such an instrument is the Wollaston prism. Why? Because it's going to refract the 2 polarization states of light in a different way. So they have a different refractive index for different polarization states. So that when your light comes in, one polarization state is going to land one part in the CCD, the other polarization state is going to land in another part of the CCD, and that's quite convenient to measure polarization. But since you need more than just 2 for obtaining all the Stokes parameter, we also put a half-wave plate that we can rotate to rotate the polarization states. And we rotate it in four directions in order to get the polarization vector. So the Q and U parameters of the linear polarization. Another key thing that you have to take into account is that since the light is gonna come up in 2 different parts, you're gonna have everything doubled. And you can see here, that's the image that I showed at the beginning. The galaxy appears twice. Every image appears twice, and that's because the one polarization state lands here, the other polarization state lands in the other. You have to put a mask to make sure that they don't overlap. And then, if you want to have the other part of the galaxy, you need to take another image afterwards, to offsetting a little bit the viewing point. Anyways, once you handle all this, we investigated the polarization, instrumental polarization of the instrument, and we found that if this is the CCD, the pixels of the CCD, sure enough, the polarization is 0 in the center. But as you move away from the center, you start finding polarizations, spurious polarizations that are none from astrophysical system, but probably coming from lens in the optical system. And it goes up to 1.2, 1.4%. So you have to really take that into account if you're looking at extended objects, or objects that cover larger parts of the field of view. You need to correct for the instrumental polarization. This shows you also the polarization as a function of radius from the center. And that's what we did for Circinus, the galaxy that I showed you before. We did correct for this effect as well. So now let me go to a second astrophysical system. So different scale, kilonovae now. And you probably heard already about kilonovae. This is the optical and infrared counterpart of gravitational wave emission from 2 compact objects that have a neutron star. So basically, either neutron star or black hole neutron star merger, right? And so you know the deal. These guys spiral in, emitting gravitational waves, shrinking, and then merging. And then thing that you have in the merger is either a more massive neutron star or a black hole you can have. But in between, you can have metastable neutron star or maybe a black hole with an accretion disk. And when people do general relativity simulations of this, these are two different simulations, these are different three times of the simulation. And you can see all this green material here is tidal ejecta, right, from the binary, in this case, neutron star merger. And some of this material can actually get unbound. And even after the merger, you can have a lot of that material around. And exactly this material that is very neutron rich is what's going to power the optical and infrared emission of the kilonova. So the kilonova basically is the radioactive decay of these heavy elements that are produced during this merger process from the neutron-rich material. So basically, you are producing a lot of R process elements, which later radioactively decay, generate a lot of gamma rays that are thermalized into optical and infrared. So what is an R process element? Here you have a periodic table, and in purple, you have what we expect. It comes from merging neutron stars. So basically, this is from the Big Bang, and all the rest are creating either stars, supernovae, or merging neutron stars. And so merging neutron stars are very important to generate these heavy elements because you need dense neutron-rich material that allows this R process, which means rapid neutron capture before there's radioactive beta decays. And so you can create these elements very fast. In particular, I want to talk about these lanthanides, which are particularly neutron-rich. And so here is a cartoon of the electromagnetic part of the kilonova of the whole system. So basically, after the gravitational waves, which is before the merger, the first thing you're going to see in hundreds of milliseconds, perhaps, is gamma ray burst. So very energetic burst that is quite debated. Suggests that it's probably coming from the accretion disk around the black hole or from a very massive magnetar, perhaps. And so that's the GRB, the first thing you're going to see. And then later on, you're going to develop the kilonova. You can also have a GRB afterglow, which can last much more days and weeks, which is the interaction of the gamma rays with the interstellar material. So, but what we're interested in is this blue and red, and these are the two kilonova components. So this red one comes from the tidal ejecta. So basically, during the in spiral, there is a lot of unbound material, these neutron stars, and that's going to be very equatorial. So that's why you're going to see it in this plane of the merger. And that one is extremely neutron rich, so it's lanthanide rich. And as I'm going to show you, it's going to be create most of the red emission of the kilonova. After the merger, right, when you have the accretion disk around the black hole, for example, then you're going to have material that is less neutron rich because there has been a lot of neutrinos from radioactive decay, so it's less dense. And then this is going to be a blue kilonova, so it's going to be ejected in the polar direction. So that's what we call the wind kilonova, right? And it's going to be lanthanide free. And so then what's the interplay with these two lanthanide materials? So the opacity is telling you how much being absorbed by the elements, the light, how much of the light is being absorbed. And we know that the opacity of electron scattering, constant scattering, as I was saying, is pretty much wavelength independent. But the atom, the line transition, so bound means atoms taking photons, right? Going from one state, from one level to another. This is going to be stronger in the blue, okay? So you're going to have much more opacity in the blue. And so you can see then basically, if you see the opacity as a function of wavelength for the two lanthanide material. So you're going to see the lanthanide rich has much more opacities, so because it's much more neutron, there are much more probabilities of line absorptions here. And in particular, you look here, this is the optical regime. You're going to see that these lanthanide rich are very opaque, whereas the lanthanide free, you're going to be able to have more emission from that material. here in the horizontal is the electron scattering. So electron scattering, as I said before, also I have to mention, is polarizing when you have reflections in the electrons. But the line transitions, you're absorbing those photons, so you're removing polarization if it was polarized at all in the first place. So this one is depolarizing. So for the lanthanide-rich material, what you're going to have then is that the line absorption is much bigger than the Thomson absorption, right, in the optical regime. And so you're going to have much more depolarization for the lanthanide-rich. For the lanthanide-poor material, then you have that the electron scattering is actually opacity is larger, and so you're going to have more polarization. Okay. And another key thing is, again, viewing angle. So if you happen to be observing at a kilonova from the polar direction, right, then basically what's going to happen is that all the photons that are coming, so this is what you see from the top. Everything, photon gets scattered here, gets scattered there into the one outside and here in the same way. So all the polarization states are going to cancel each other. So basically you have a net polarization of 0 if you're looking at it from the top. But if you're looking at it from the edge, that's not going to happen because this is not symmetric, right? You have this direction is going to be not canceling out, right? So at the end, you're going to have a net effect of polarization. So the viewing angle is very important. And so here again, we did 3D Monte Carlo radiative transfer simulation. And you can see that the prediction of the polarization as a function of wavelength. As I told you, the lanthanide, this is a lanthanide mix, lanthanide rich. And so in the optical, so this is here infrared, this is optical. In the optical, we know that the lanthanide free are more polarizing, so you're going to get a higher degree of polarization. Whereas for the lanthanide rich in the optical, you don't have. Now in the infrared, they both have very low opacities. So if you remember here in the infrared, they're both basically 0. And so it's just basically scattering. But then here again, you have the effect that this guy is not, you're observing it, if you observe it, it's a bit more polar, so you won't have the same effects of the geometry, right? And then for the lanthanide rich. So that's why in the lanthanide rich get more polarized if you look at it in the infrared. What happens if you look at it as a function of angle, for example? So this is the equator, looking at it edge on. So that's where you're going to have the highest polarization, as I was saying before. If you look at it polar, then you have the lowest polarization. You can also look at it through evolution of time. The kilonova is evolving. So at the beginning, it's brighter. With time, it gets fainter, but also gets cooler. And with cooler, the opacity increases, right? And so you're going to have more depolarization effects. So that's why at the beginning, it's higher the polarization, and as time goes by, the polarization of the kilonova goes down. So if we want to observe a polarimetry for kilonova, we have to observe them early on. And that's tricky. And tricky is also that we don't have a lot of data. This is the only kilonova we've observed, 2017 GFO, or at least the one with the strongest flames. This one is clear because we observe the gravitational waves, we observe the GRB, and we observe the kilonova a lot. Optical, spectra, infrared, photometry, everything. And what we measure is 18%, 0.18% polarization, very low. So this puts a limit here. So basically, this means we can discard, because we observe it also quite early, 1.5 days. So we can discard all of these viewing angles. So we know that this kilonova, we were observing it at within 65 degrees of the pole, right? So that's kind of interesting, and it agrees very well, this angle, with some other studies of the GRBs, for example. So it's not the only way to constrain the angle, the viewing angle of the kilonova. So, but really, we only have one data. Can we get more data? Well, the good thing is that 04, yes. Because this is the highest polarization we have. And this is for the first, we also have date at 1.5 days. Yeah, okay. Yeah, it has to be smaller, so it cannot be this high.
Okay, but suppose it's like between 1.5 and 10 days.
Yeah, and this is at 1.5 days, this observation.
Okay, so 1.5.
So basically, we're only using this to restrict this. We're not using these two other epochs. So from this epoch, we can conclude that. Okay, so good thing. 04 LIGO run is starting next week, and it's gonna have higher sensitivity. You're gonna reach to longer distances, so increasing your volume, increasing the probability of detecting kilonovae, and that's very cool. And I'm part of this engraved collaboration, which is the electromagnetic follow-up of candidates, which is tricky because LIGO and all this gives you a large region where there's millions of galaxies, so it's not easy. Even with the GRB counterpart, the region, probability region of where it's located is also very large. So it's very hard, but it's doable, as one example showed. And the good thing is that we have access to a lot of data, but especially also force-2 data, polarimetric data. And so we can trigger them as soon as we have good candidates. And yeah, so here we're talking about 0.18 for this case for polarization, but really this assumes that interstellar polarization is very low. Interstellar polarization is another thing that creates polarization, and it's dust in the line of sight. And I'm going to talk about that. So this is the galaxy, the whole galaxy of that kilonova event. Right? It happened actually here. And I don't know if you can see from there, but this is the whole galaxy. There's some brown lines there, right? That's dust. Here we don't see it, but it doesn't mean there isn't. Dust is always somewhere around. And those dust can also create polarization. That is not from the source itself, so it can through our measurements, right? And the way this happens is that if you have unpolarized light, right, and you have some dust particles that are maybe not spherical, they're aspherical, right? And they get aligned with the magnetic field of the galaxy, so an external magnetic field. And then what happens when the light comes in is that this electric component that is parallel to this elongation is going to be absorbed. And so at the end, what's going to go through is a linearly polarized light, right? That's what you're going to see in the optical or the infrared. Those same particles afterwards re-radiate at longer wavelengths, sub-millimeter, but now they're going to re-radiate in the direction they absorb. So it's going to be completely perpendicular to the polarization state that you measure from the optical wavelength, right? So you can see the dust, how the dust polarizing both in the optical or in the sub-millimeter. And how can we then fix for this problem? Well, also because the problem is that there's dust not only in the host galaxy of the event, but also in our Milky Way there's dust. So you have twice the problem of dust during your observations. So what you can do is that in your field of view, there are perhaps a lot of other stars that are shown there by circles that are even, and you can match those stars to see if they're part of with a catalog, if they're part of our Milky Way. And if they're part of the Milky Way, you measure their polarization, and then you know the polarization of the Milky Way. So that's one way to get the polarization of the Milky Way. Here, each point is a star in that field of view. Here you have U and Q, the Stokes parameters. If you correct them for the instrumental polarization, which means this star that is at the edge, remember there is a spurious instrumental polarization at the edge, so you need to correct for that. So once you correct for those, you can see that they're tighter, packed together, and you can get the median of that value. That's what we are gonna assume is the interstellar polarization from the Milky Way in that particular image. And you can plot the polarization as a function of wavelength and for different filters, and they have this typical relation. It's called a Sarkovsky relation, which is typical from dust. And the point where this peaks is related to the dust particle itself, this dust size. And you can compare this to the submillimeter, because then afterwards the submillimeter should have the same polarization, but only in emission. And in fact, this is from a Planck map. You can see that it agrees very well from the optical polarization from the stars, that agrees with the Planck maps at that position of the sky. So there are ways to correct for the interstellar polarization of the Milky Way. How about for the host galaxy? For the host galaxy, the problem is that you cannot resolve those stars. Those stars are far away, the stars of that other galaxy. So it's difficult. So you can use integrated light, and this is what these people have done here. You can see the polarization line, a very dusty Centauro galaxy, and you can see that the polarization is strong throughout dust lanes, right? And basically, this is what we want to do, but for our galaxies that are host of the kilonovae or supernovae. And this is work that is on progress. We have 12 host galaxy, and this is work done by Joao Silvestre. Here is some preliminary result where you can see, for example, different positions of the galaxy, right? And you can calculate the polarization from that integrated light as a function of wavelength for those 4 positions. And you can see they follow a stochastic law, which is the law that we expect from the dust. Okay. So how am I out of time? 10 minutes. 10 minutes. Okay. So let me finish then with supernovae, which is the reason why I started working in polarimetry at first. So you know, there are many types of supernovae, and polarimetry is useful for all of them, but I will talk mostly only about type 1 supernovae, which are very bright, and you perhaps have heard them because they use them for measuring distances in the universe, because they're very homogeneous. Their light emission is very well known, and typically they last several months. They reach a peak after a couple of weeks, and then they decay for months. And you can keep observing them if they're very nearby, even years. And many hundreds of years later, you see the supernova remnants. This is the ejecta interacting with the interstellar medium. And the light is generated also by basically similar to the kilonovae. You generate through nucleosynthesis also heavy elements, our process elements, although less neutron rich than the kilonovae. And the radioactive decay gives you the energy of the supernova. We know that, but we don't really know the progenitors. We use them for cosmology. We only know that they occur in binary systems and that it's a white dwarf. But we don't know what's the companion. And there are many scenarios for the progenitors, but people class them in 2. One is the single degenerate, so basically the companion is a non-degenerate star, main sequence, or a red giant that donates mass to the white dwarf, which near the Chandrasekhar limit, and then goes to a thermonuclear runaway. The other typical scenario is another white dwarf, which, similar to 2 neutron stars, they merge, emitting gravitational waves. And then sometimes, I mean, they can explode in this way, or one of the white dwarfs can also donate material to the primary star, which detonates in the outskirts and leads to a secondary detonation in the center. So those are the 2 main scenarios, and people debate. Maybe it's a combination of the 2 that actually happens, or maybe it's only one. There are evidence for one, evidence for the other. In particular, I want to talk about one diagnostic, which is the circumstellar material. So if circumstellar material refers to material that was ejected from the progenitor before the explosion, right? And this would happen mostly actually for this single degenerate, because this can have a lot of winds, and through this matter donation, you can have more material that is surrounding. And if we find this material, then probably this is one evidence for this scenario. And so there have been claims for such an observation. And what can polarization tell us about this? Well, again, the same key thing: if you have circumstellar material that is symmetric, or ejecta that is symmetric, then if you're observing it from this side, everything that gets scattered this will cancel with this one, right? Sorry, this one will cancel with this one. This one will cancel with this one. Net polarization 0. If it's a bit asymmetric, that's circumstellar material or CSM, then you're going to have more arrows. This one is not going to cancel with anything. You're going to have a linear polarization, right? You can even try to infer the composition of that circumferential material. And if you have, for example, a cloud of, let's say, hydrogen, an element that is there, but not in the rest, that is more concentrated in a particular region, then also the reflections of hydrogen are not going to be symmetric, and you're going to have line polarization. So you're going to have polarization in particular lines. Even though the continuum polarization is going to be symmetric because of this. If you have both something asymmetric in the line and the continuum, you have both cases of polarization. So here are some observations from type 1a supernovae. Here on the x-axis, you have polarization degree measured to some of these type 1a supernovae. On the y-axis, you have AV. AV is the quantity of absorption of dust, right? And so it's interesting because it's telling you that the more polarized the supernovae actually suffer more from dust extinction, which is something that I already mentioned. And it sort of makes sense, but it's quite a strong relation. And also, if you look at the polarization as a function of wavelength, this is for a star in the Milky Way. Remember the Cherkovsky behavior that I showed you before. It follows this, whereas for some supernovae, you find a very strong increase in the blue that is not very easily explainable with dust particle differences, which is what you would expect in the Cherkovsky model. So maybe this is telling us something about the circumstellar material as well. So again, some Monte Carlo radiative transfer for supernovae. You have to model your supernova. It's going to explode in the center, and you have to model the circumstellar material around. It can be a disk, or it can have another different shape. If it's symmetric, then you don't have the polarization thing. And here is some modeling that you can see depending on where you put the CSL. So if you put it very far from the explosion, then at the beginning, because of the low scattering angle, you're not going to see any polarization, right? But as the light, the light starts coming closer to the CSM, right? Then depending on the viewing angle, if you're looking at it edge on, again, you're going to have high polarization. If you're looking at it from the polar direction, you're going to have very little polarization. So, I mean, you can model the structure or the CSM structure that you want, but if you have something asymmetric, you're going to have imprints in your polarization evolution. You can also see it here. This is Q and U plane. So the lines are the polarization vectors, and you can see that at the beginning you don't see anything. With time, the polarization increases, and the angle of the polarization is always the same. If there was an abrupt change of polarization direction, this could be telling you something of different physical systems. And you can see that there's a change with wavelength as well. So there's more polarization in the U, and so in the bluer bands, exactly like what we are observing here for the supernova. The problem is that we have very little data, polarimetric data for supernova. Again, that's like for kilonova. There's only like a polarization one per the whole per supernova, so we don't have the evolution, right? And that's because mostly people have focused on spectral polarimetry, which is getting the polarimetry for the full spectrum at every wavelength, and that's very expensive. You need very nearby because it's very difficult to observe, and you need a lot of telescope time. So maybe imaging polarimetry is better and it's cheaper, and that's why we are having a program to observe supernovae with CAFOS, which is an instrument in Calaralto in Spain. We have already observed around 10 type 1a supernovae, and 2 of them are very reddened with a lot of extinction, so probably good candidates for this circumstellar material around them. And because I promised a third production, I'll briefly mention background sky polarization. So, you know, when you're observing, you have in the field of view your star or whatever, and around there is sky. This sky, there's also photons, and sometimes these photons are polarized. And if they're there, probably they're also in your source, and you need to correct for that, right? Where does that sky polarization come from? Well, there's many possibilities, but one very clear is the moon. So if you're observing at night and the moon is in the sky, right? Even if it's not in your field of view, the moon emits photons that reflect in the atmosphere and go into your line of sight. and this can get, especially at that reflection, it can get polarized, right? And depending on the atmosphere particles, so you have air molecules, but you can have aerosols and clouds. That depends also on the position of where you're observing. And so Beatriz Pereira actually is analyzing from Paranal, developing two models, one of single scattering and another of multiple scattering. So here's the moon. So basically, you're sitting on Paranal. This is what you see in the sky. And this is the moon position. And you can see that the highest polarization, as you know, is at 90 degrees because of scattering, right, in the atmosphere. And the lowest is close to the moon, or at the other side of the moon. So it's interesting because normally, for normal observation, you don't want to have the moon very close because it's a lot of light. But if you want for polarimetry, it's actually, despite there is a lot of intensity, but there is less polarization close to the moon. Right? Obviously, the best is there is no moon. This is a multiple scattering model, and you can see that instead of having one neutral point means zero polarization. There's actually 2 points of zero polarization. So meaning when the light actually interacts more than once in the sky with the sky particles, your pattern of polarization is going to be different. And also the maximum polarization is much lower. You get a lot of depolarization to multiple scattering. And so we actually got data to compare her models from Paranal. And they actually work quite well with the single scattering model for the bluer wavelengths. But for the redder wavelengths, it's better with the multiple scattering model. That actually makes sense. Why? Because redder wavelengths, your light is going to interact with bigger particles, right? And the bigger particles in the atmosphere, you have a bigger cross section, but bigger probability of interacting. So it makes sense that a redder wavelength, the multiple scattering is stronger. And then you can predict with these models what you're going to observe from Paranal, right? Paranal at a given day and at a given position, you can know exactly what's the moon the moonlit polarization of the night. It's basically constant. Here you see a change, but this is very low percentage of polarization, lower than what you actually can measure. So I'm going to conclude. So I think I've shown you that optical linear polarimetry. I hope I've shown you it's tricky. There's a lot of contamination that you should be aware of and consider and correct or have upper limits. And those are the instrumental polarization, which generates polarization at the outskirts of your CCD, and that depends on the instrument. But then you also have the interstellar polarization from dust, both from your Milky Way and from the host galaxy that you're observing, and you need to take that into account. And then you also have sky polarization, which can come from the moon, and you should also correct for that. But if you are able to do this, I think optical linear polarimetry is very powerful, as I've shown you. It can reveal structures that are obscured behind the dust, like the broad line regions and AGNs. It can disentangle the orientation and geometry of structures, right? So if you're looking at edge on or face on for the kilonova or for the CSM in the type 1 supernovae, but it can also constrain the composition, like the lanthanides elements, or also some of the CSM elements in the supernova. So thank you very much, and I'll take questions. Right on time, thank you.
As far as I understand, the magnetic field of the galaxy is correlated with the kilometer.
Yeah.
What can we learn about the magnetic field?
Yeah, that's the very, it's used for magnetic fields as well. I didn't mention that, but yeah, absolutely. So you saw it in that, yeah, here, for example. So it turns out that normally the magnetic fields are actually aligned with this parallelogram. And so if you find that your polarization in the optical is actually parallel to the dust, it probably means the magnetic lines are going to be there. Here, this is another effect probably. This is scattering, which is more complicated, because the good thing about these is that we're looking at it directly, so you're not going to have any scattering, right? But these guys, they're going to have light from here that is coming towards scattering. So here you have a mixture of scattering and the effect of the dust particles aligned with the magnetic field. You can see that, yeah, here as well. So basically, the magnetic field aligns those particles, right? This is the magnetic field from the galaxy. And so basically, your polarization state in the optical is going to be parallel to the magnetic field, perpendicular to the axis, the long axis of the dust. But people are using this to measure magnetic fields, or they have used in the past. We've discovered the withdrawal that people are not working in this for 20 years now. So we have now better instruments, something worth to look at. Yeah. Other questions?
First, you show correlation. Well, I know correlation about the
Yes. Yeah, so I don't think there is anything that polarization can tell you, although about the mass of the supermassive black hole. I mean, yeah, sure. There is a very known correlation between the mass of the black hole and the mass of the bulge or the galaxy. Yeah, I think yeah, with polarimetry, I don't know anything that has done about this with mass, but as there is little, in general, little study, especially of a galaxy. Polarization have been mostly used, yeah, a bit for AGN, especially for this kind of finding the polarized flux of type 2 AGN and stuff like that. But this tells you mostly about the broadline regions, but it doesn't tell you anything directly about the supermassive black holes. Yeah, I mean, yeah, I mean, this is how I always try to sell the cosmology always sells, and we need what type 1a supernovae. The biggest systematic nowadays is that we don't really understand. One is the color, and there's a type 1a supernova are not perfect standard candles, which means the brightness needs to be corrected for, right? And you need to correct for one is the color luminosity relation, right? And that correction is very uncertain, especially because we assume a lot of things that are the same, but we don't really understand that color luminosity has a dust component in it. And because we don't understand colors, we don't understand if there's dust nearby this supernovae that that varies this color, right? So understanding where these colors or where the extinction comes in is crucial. And polarimetry can definitely help you because, as I showed, you can see if there is nearby dust. With these last plots that I was showing you, the idea is to try to, at the end, figure out what kind of dust is around supernovae. Is it nearby or not? Right? So these kind of things are going to help you because these CSM, these are basically dust structures, and these dust structures absorb your light, so they make your object fainter but also redder. And that correction of the reddening, you're using it, and maybe you're using always the same correction, when in reality, not all type 1a supernovae have the same CSM. Not all have CSM, so it's very dangerous, the corrections that we do for cosmology and for the Hubble tension. So yeah, definitely.
I didn't understand why the broad lines
yeah, I didn't say that. I forgot. Yeah, good point. So the broad line, they're closer to the accretion disk, and the accretion disk is actually rotating very fast, right? So you have a lot of Doppler shifts from this gas, so that makes it broad. That's the reason. Whereas the narrow line emissions are much further away, so you don't have. They're colder, and they've already lost this Doppler shifts. No further questions. Actually, I have one
because I think I don't understand that part. For the kilonovae, what besides the orientation, what exactly the polarization? Is there anything unique polarization that should tell you something about the kilonovae?
Yeah, so there's several things. There are, I would say, yeah, I can tell you the orientation for sure. That's one, but also the composition. So you can see the
Is
polarization.
that unique polarization or?
Not only. So I didn't show you this, but I can show you. Sorry. Sorry. It's at the end. Yeah, here. This is the actual data from the kilonova. This is light burst, so the evolution of the brightness in different filters as a function of time, and the points are the data. And these are different models. And basically, the blue. So there is only blue kilonova, only red kilonova. So only lanthanide free and lanthanide rich, and there is this red one, which is a combination of lanthanide rich for lanthanide mixture. And so the thing is that the blue part, these are very blue, cannot be explained by lanthanide material because there's a lot of opacity. And this is normal intensity. So also from intensity, you can also get an idea of the composition. So it's complementary. And at the same time, the infrared, you cannot explain it with only a blue component because you need a lot of lanthanide rich material. So that's why this kilonova was an example of we need to have both the kilonova, the tidal ejecta kilonova, and the wind kilonova. Both components should contribute to the emission. And the polarization confirms this in this case. It's not unique.
Yeah.
The angle, you cannot get the angle.
Yeah,
the angle is completely polarized.
Thank you.
By the way, this is also spectra that we took, and you can model the spectrum. You can see elements that are completely our process elements. This was one of the key signatures in spectra. Okay, sorry.
No, thank you very much. If there are no further questions, I think we can thank Santiago again.
If you enjoyed the video, like and subscribe.